So, good morning. Let's continue our discussion on the Riemann-Stieltje integral, Riemann-Stieltje integral. Okay, so let's see the next theorem. So it says, so it is lower Riemann sum FD alpha is always less than or equal to upper Riemann sum FD alpha. Okay, proof. So let P1 and P2 be any two partitions of closed interval a comma b, and let P is equal to P1 union P2, then P is nothing but the common refinement. The common refinement of P1 and P2. You know what is refinement? Then L P1 F alpha is always less than or equal to L P F alpha. Why? Because P is the refinement of P. Therefore, number of points in P is more than number of points in P1. Therefore, if I increase the number of points, partitions, then lower sum getting increases. So now also lower sum is that's lower sum is also less than or equal to UP F alpha. Again, this is also less than or equal to UP2 F alpha. How? P2 is P is the refinement of P. Hence, UP F alpha is less than or equal to UP2 F alpha, because in P number of points again increases. Is more than number of points in P2. Now this we have. Wait a second. This we have L P1 F alpha is less than or equal to U P2 F alpha. Okay, now keeping this P2 fixed, and varying P1 ಅನ್ನು vary ಮಾಡ್ತಾ ಹೋಗಿ. Now as you vary this P1, since P2 is fixed and since it's a sum of the areas of lower rectangle, this is always less than or equal to this sum of the areas of upper rectangle. Therefore as I vary P1, this will, since it is fixed, this will be this right hand side. This will, as I vary P1, since this P2 this one is fixed, this will become an upper bound of this one. Therefore, if I take the supremum of this LPF alpha, then since supremum is a least upper bound, this one is less than or equal to UP2 F alpha. Supremum of LP1 F alpha is less than or equal to UP2 F alpha. Now, what is supremum of LP1 F alpha? It is nothing but lower Riemann sum integration a to b fd alpha. So I got integration a to b, that is lower Riemann sum, is less than or equal to integration a to b fd alpha, which is less than or equal to u P2 F alpha. Now where is this P2? Where is this P2? P2 is a partition of closed interval A comma B. As I vary this partition of this P2, this sum of the rectangles, areas of these rectangles will always greater than or equal to this lower Riemann sum. It's always greater than or equal to Riemann sum. Therefore, if I take this quantity, this lower Riemann sum becomes infimum of theta called up to f alpha, where p2 is the partition of closed interval a comma b. It's a lower bound. Therefore, if I take the infimum of u p2 f alpha, that is greatest lower bound, this will be greater than or equal to lower Riemann sum integration a to b f d alpha. And what is infimum of u p2 f alpha? It is nothing but integration a to b upper Riemann sum f d alpha. Thus we got lower Riemann sum is less than or equal to upper Riemann sum. Hence the result. So even though see, if I say this is lower Riemann sum, this is upper Riemann sum, actually since it is fd alpha and it is so this has to be this is nothing but Riemann Stieltjes lower Riemann sum, and this one is Riemann Stieltjes upper Riemann sum. Okay, so make out this difference. So let's move forward. The next theorem. This theorem says, okay, so let f be a bounded real valued function. So let f be a bounded real valued function. It's a real valued function on closed interval a comma b. Closed interval a comma b and alpha b monotonically increasing function on closed interval a comma b. The result goes like this. This is the hypothesis, and the result is f belongs to R of alpha, that is f is Riemann Stieltjes integral if and only if for every epsilon greater than 0 there exists a partition P of closed interval a comma b such that u p f alpha minus l p f alpha is less than epsilon, and this result is known as Riemann criteria for integrability. It is known as Riemann criterion for integrability. Okay, so let's prove this. Proof. Okay. So we shall prove the converse first by assuming that for every epsilon greater than 0 there exists a partition P of closed interval a comma b such that u p f alpha minus l p f alpha is less than epsilon. Hence we shall prove that f is Riemann Stieltjes integral. So the first thing is to observe is from the above result, that is lower Riemann integral. So here I am considering again Riemann-Stieltjes integral. So let's lower Riemann integral. So lower Stieltjes integral is less than or equal to upper Riemann-Stieltjes integral. Now, what is this upper Riemann-Stieltjes integral? This is nothing but supremum upper Riemann-Stieltjes integral is nothing but it is infimum of UP of alpha. Infimum of UP of alpha. This is nothing but infimum of UP of alpha. So, what is infimum of what then? Then infimum of UP of alpha means it is the greatest lower bound. So, if I consider any other lower bound, then this one is less than or if I consider any other partition, then it is less than or equal to UP of alpha. Similarly, this is nothing but supremum of LP of alpha, or it is, we can say it is greater than or equal to LP f alpha. So let's remove this and say, so for any partition, P of closed interval a comma b, we have LP f alpha is less than or equal to lower Riemann-Stieltjes integral, which is less than or equal to upper Riemann-Stieltjes integral, which is less than or equal to UP f alpha. Let's name this as star. Okay. Now for any epsilon greater than 0, by assumption, see, for if I take any epsilon greater than 0, say let epsilon greater than 0, then by assumption there exists a partition P such that UP of alpha minus LP of alpha is less than or equal to. So using this assumption, say there exists a partition P. This partition is existing with respect to this epsilon. So we shall say it is P of epsilon. So epsilon greater, there exists a P is equal to P of epsilon, such that so since this P is existing with respect to this epsilon, we are naming it as P of epsilon. So such that by the given assumption UP f alpha minus LP f alpha is less than epsilon. So we name it as double star. So this star, the equation star, or the expression star holds for any partition of closed interval a comma b. Therefore, in particularly, my double star is also holds for this partition. Is also hold for the partition P of epsilon. That is, so using star. So that is upper Riemann sum integral a to b upper Riemann-Stieltjes sum minus lower Riemann-Stieltjes sum. So we can say this one is greater than 0, and since it is less than or equal to this, so this one is less than or equal to, now it is less than or equal to UP f alpha. Again, this lower Riemann-Stieltjes sum is greater than or equal to LP f alpha, but since it's a minus, we can say it's minus LP f alpha, and by this double star, this one is less than epsilon. So that is we got it's 0 less than or equal to lower upper Riemann-Stieltjes sum fd alpha minus lower Riemann-Stieltjes sum fd alpha is less than epsilon. Now since this epsilon greater than 0 is arbitrary, or since this is holds for every epsilon greater than 0, we must have lower Riemann sum and upper Riemann sum must be equal. That is, upper Riemann-Stieltjes sum is equal to lower Riemann-Stieltjes sum. This implies your f belongs to R of alpha. That is, f is Riemann-Stieltjes integrable. Hence the converse part. So now let's see the direct part. So by Assume that now f belongs to R of alpha, and let's prove that f satisfies the condition, that is for every epsilon. We shall prove this for every. We shall prove that for every epsilon greater than 0, for every epsilon greater than 0, there exists a partition P of closed interval a comma b such that UP of alpha minus LP of alpha is less than epsilon. Okay, now, so let epsilon greater than 0 be given, and Riemann, Riemann-Stieltjes integral FD alpha is nothing but, so this is a common value of Riemann, lower Riemann-Stieltjes integral, or and upper Riemann-Stieltjes integral. So that is nothing but supremum of LP f alpha for every partition P of closed interval a comma b, and also it's equal to infimum of UP of alpha. So for time being I'm taking that LPF. So therefore if I take integral a to b fd alpha minus epsilon by 2, so supremum of LP of alpha, that means this is the lowest upper bound or the least upper bound. Integral a to b f d alpha is nothing but now it's the least upper bound, least upper. So if I subtract a quantity that is minus alpha epsilon by 2, this will be cannot be an upper bound. It's a cannot be an upper bound. So it cannot be an upper bound of the set of all LP of alpha. Such that B is a partition of closed interval a comma b is a partition of closed interval. So this is cannot be an upper bound. So this is not an upper bound. That means, so there exists a partition P1 of closed interval a comma b such that it is not an upper bound. That means there is not an upper bound, means there is some element in this set which is greater than this element. So in this element means it's LPF alpha, it is existing with respect to the partition. So there exists a partition P1 of closed interval a comma b such that integration a to b fd alpha minus epsilon by 2 is less than LPF alpha. Similarly, this Riemann-Stieltjes integral FD alpha, it is nothing but infimum of UP f alpha. That means this is the greatest lower bound. Hence, if I take integral a to b fd alpha plus epsilon by 2, then this is not a lower bound. So not a lower bound of set of all UPF such that P is a partition of closed interval a comma b. So it's not a lower bound, means there exists a partition P2 of closed interval a comma b. That means it's not a lower bound, means there is some element in this set which is less than this element. So this element in this set, the element exists with respect to the partition. So there exists a partition P2 of closed interval a comma b such that say UP2 f alpha is less than integration a to b fd alpha plus epsilon by 2. Now here we got two partition P1 and P2. Using that, I am constructing a new partition P1 union P2 and naming it as P, where this P is now the common refinement of P1 and P2. Now if I consider UPF alpha, then see, this P is the refinement of P1 and this also P2 is a common refinement of P1 and P2. So if I consider UPF alpha and UP2F alpha, then the difference is less than or equal to, because in P the number of points are greater than or equal to number of points in P2. Moreover, P is the refinement of P2. So again, this UP2F alpha is now less than or equal to, by this it is integration a to b fd alpha plus epsilon by 2. Now again, so again, integration a to b f d alpha minus epsilon by 2 is less than L P1 f alpha. So that means this quantity is now less than sorry, it's now less than, wait a second. Yes, now this quantity is less than L P1 f alpha plus epsilon by 2, again plus epsilon by 2, this will be plus epsilon. So now again P1, P is the now refinement of P1, so it is now less than L L less than or equal to LP f alpha plus epsilon. So by using this two, we have, second, we have U P f alpha minus LP f alpha is less than epsilon. We have their difference is less than epsilon. Now since this epsilon is for every epsilon greater than 0, so yeah, for every epsilon greater than 0 there exists a partition P of closed interval a comma b such that UPF alpha minus LPF alpha is less than epsilon, hence the results. So now again let's move forward. So the next result is again a theorem. So this theorem says, let f be a bounded function. So let f be a bounded function on closed interval a comma b, and alpha is monotonically increasing okay. Before proving this, let's so this criteria, that's Riemann criteria for integrity, this will help in proving some of the results. So in next coming classes, so it is enough to prove, say, f is Riemann Stieltjes. To prove f as a Riemann Stieltjes integral, it is enough to prove this. For every epsilon there exists a partition P of closed interval a comma b such that UPF alpha minus LPF alpha is less than epsilon. Now, so this result, so f be a bounded function on closed interval a comma b and alpha is monotonically increasing on closed interval a comma b. So there are three results. That's if UPF alpha minus LPF alpha is less than epsilon, See, this is star. This is holds for some epsilon greater than 0 and some partition P of closed interval a comma b, then it holds for every refinement of P with the same epsilon. ಸೇಮ್ ಅಂದ್ರೆ ಈಗ ಸಪೋಸ್ ಒಂದು epsilonಗೂ ಒಂದು ಪಾರ್ಟಿಷನ್ಗೂ ಇದು ಹೋಲ್ಡ್ ಆದ್ರೆ ಆ ಪಾರ್ಟಿಷನ್ ನ ಯಾವುದೇ ರಿಫೈನ್ಮೆಂಟ್ ತಕೊಂಡ್ರು ಇದು ಈ ಎಕ್ಸ್ಪ್ರೆಷನ್ ಏನ್ ಹೇಳುದು, ಈ ಕಂಡೀಷನ್ ಸ್ಯಾಟಿಸ್ಫೈ ಆಗ್ತದೆ ವಿತ್ ದ ಸೇಮ್ epsilon ಚೇಂಜ್ ಆಗ್ಬೇಕಾಗಿಲ್ಲ. ಅಂಡ್ ದ ನೆಕ್ಸ್ಟ್ ಒನ್ ಸೇಸ್ if star holds for the partition, if star holds for the partition P is equal to x0, x1 and so on up to xn of closed interval a comma b and si ti are arbitrary points in xi minus 1 comma xi 1 less than or equal to I less than or equal to n, then summation modulus of f of ti minus f of xi into delta alpha I, where I is from 1 to n is less than epsilon, and third one, if f belongs to R of alpha, that is f is Riemann-Stieltjes integral, and the hypothesis of B holds, that means if star that is the star, that is again UPF alpha minus LPF alpha is less than epsilon for partition P is equal to x0 x1 xn of closed interval a comma b, and SITI are arbitrary points in closed interval xi minus 1 comma xi, then summation I is equal to 1 to n modulus of summation I is equal to 1 to n f of ti delta alpha I minus integral a to b f d alpha is less than epsilon. So let's prove one by one. So the proof of A. So it says suppose UPF alpha minus LPF alpha is less than epsilon for some epsilon greater than 0 and some partition P of closed interval a comma b, that is UPF alpha minus LPF alpha is less than epsilon for some partition P of closed interval a comma b and some epsilon greater than 0, So let P star is the refinement of P star be any refinement of P, then using this refinement, if LPF alpha, the relation between LPF alpha and LP star F alpha is nothing but it's less than or equal to, because P star is the refinement of P. Now again, sum of areas of lower rectangle is always less than or equal to sum of areas of upper rectangles with respect to the same partition. Again, since P star is the refinement of P, sum of areas of upper rectangles with respect to P star is less than or equal to UP F alpha, as P star is the refinement of P. Now using this relation, UP star F alpha minus LP star F alpha. Now this one is less than, now UP star F alpha is less than or equal to UP F alpha, so it is less than or equal to UP F alpha, but LP star F alpha is greater than or equal to LP F alpha, since it's a minus of LP star F alpha is less than or equal to minus LP F alpha, so it is minus LP F alpha, but given that it is less than epsilon, so with respect to the same epsilon we got for the partition P star, that is nothing but a refinement of P, we got UP star F alpha minus LP star F alpha is less than epsilon, okay. So let's see now question 2 now. So assume that here also UP F alpha minus LP F alpha is less than epsilon for partition P is equal to x0 x1 and so on xn of closed interval a comma b, is partition P is nothing but x0 x1 x1 xn of closed interval a comma b. Now let Si and Ti are 2 points in xi minus 1 and xi, the smaller interval, for all I between 1 and n. Then see, so see, let's draw. See, if I have this and I have some partition, say this is A and say this is B. So this is now xi and this is now say xi minus 1, this is xi. So Si and Ti are the 2 points. Say this is Si, say this is Ti, are the 2 points in between xi minus 1 and xi. Then if I take f of Si and f of Ti, so these two, they will be lies between say in this interval xi minus 1 and xi. Say the smallest value is something, say this is the smallest value, and then let's denote it by mi, and the largest value, that's the infimum, supremum is nothing but capital Mi. So you already seen, so we can say this one, f of Si and f of Ti, they will belongs to closed interval mi, small mi comma capital Mi. Then what is mi? Small mi, it is nothing but infimum of f of x, where xi minus 1 less than or equal to xi, less than or equal to xi, and what is capital Mi? It is nothing but supremum of f of x, where xi minus 1 less than or equal to x, less than or equal to xi, and this is true for all I. For all I. Now, so if I find the difference of this f of Si minus f of Ti, so their difference, see, is they are the two values between f of Si and f of Ti. F of Si and f of Ti are the two values between Mi and small mi and capital Mi. So their difference will be less than or equal to capital Mi minus small mi, and this is true for all I between 1 and n. Okay, now therefore if I consider the sum of all this for considering finding this for each I and taking the sum, it is summation f of Si minus f of Ti, modulus of f of Si minus f of Ti, which I is varying from 1 to n. This will be less than or equal to summation, okay, into delta alpha I, sorry, into delta alpha I, and I is nothing but 1 to n into, now it is mi minus small mi into delta alpha I. So if I split this, this one is nothing but summation capital Mi into delta alpha I is equal to 1 to n minus summation I is equal to 1 to n small mi into delta alpha I. Now what is this summation capital Mi into delta alpha I? This is nothing but u p f alpha, and this is nothing but LPF alpha, small mi into delta, summation I is equal to 1 to n small mi into delta alpha, LPF alpha, it is now less than epsilon, it's now less than epsilon. So I got this relation is less than epsilon. That's what I need to prove in this case. Yes. Now we shall prove the third one, that is if f is a Riemann-Stieltjes integral and the hypothesis of B holds. Let's prove this relation. Okay. Okay. So see that. So again, assume that UPF alpha minus LPF alpha is less than epsilon. For partition P is equal to, yeah, same, it is x0, x1, so on up to xn of closed interval a comma b, then epsilon greater than 0 and then epsilon greater than 0. Let Ti belongs to xi minus 1 comma xi for all I, is you already see in part B, and then since F is Riemann-Stieltjes integral, f belongs to R of alpha, we have LPF alpha is less than or equal to integration a to b f d alpha, which is nothing but less than or equal to UP f alpha. So let's name this as equation number 1. Now since Ti is in xi minus, between xi minus 1 and xi, we can see this your f of Ti will be lies between small mi and capital Mi for all I, and you know what is mi and capital Mi. Small mi is nothing but infimum of f of x in the interval xi minus 1 and xi and capital Mi is nothing but supremum of f of x in between xi and xi minus 1. Now LPF alpha is nothing but summation I is equal to 1 to n. It is small mi into delta alpha I. Now, if you observe from this mi is less than or equal to f of ti, therefore this one is less than or equal to summation I is equal to 1 to n. It is f of ti into delta alpha I. Again, this f of ti is less than or equal to mi, that is less than or equal to summation I is equal to 1 to n capital Mi into delta alpha I. Now, what is this? It is nothing but UPF alpha, UPF alpha. That is I got LPF alpha is less than or equal to summation I is equal to 1 to n f of ti delta alpha I. That is, this one is less than or equal to this one, and this less than or equal to this less than or equal to UPF alpha, UPF alpha. So it's like 2. Now observe equation relation 1, that is LPF alpha is less than or equal to integration A to B f d alpha, which is less than or equal to UPF alpha, and using the expression 2, we have modulus of summation I is equal to 1 to n f of ti delta alpha I minus integration A to B f d alpha is less than or equal to UPF alpha minus LPF alpha. So see, these two quantities, this quantity as well as this quantity, there lies between LPF alpha and UPF alpha. So their difference and modulus of their difference is also lies between UPF alpha is always less than or equal to UPF alpha and LPF alpha minus LPF alpha. So, but using my assumption, this one is less than epsilon. Hence, I got this relation is less than or equal to less than epsilon. This is what I need to prove in this. Hence the result. Okay, so let's see one more result. It's a smaller one of the beautiful and interesting result. So this is the theorem. So it says, so if f is continuous on closed interval a comma b, if f is continuous on closed interval a comma b, and alpha is monotonically increasing, and alpha is monotonically increasing on closed interval a comma b, then f belongs to R of alpha on closed interval a comma b. If I have a continuous function, just a continuous function, then it is Riemann integrable. If I have a continuous function and alpha is monotonically increasing, then f is Riemann Stieltjes integral, or f belongs to R of alpha. So let's prove this now. So to prove f, so as you've seen in a Riemann criteria, so to prove f belongs to R of alpha, it is it's enough to verify that Riemann criteria of integrability. So that is enough to prove that for every epsilon, greater than 0, there is a partition such that difference of UPF alpha minus LPF alpha is less than epsilon. Okay, so let epsilon greater than 0. Now since f is continuous on closed interval a comma b, now f is continuous on closed interval a comma b, and if you observe this as a closed interval, and it's a compact, therefore we can say f is bounded and uniformly continuous, continuous. So choose a real number, say eta greater than 0, such that eta into alpha of b minus alpha of a is less than epsilon. So choose such an eta. Okay, now since f is uniformly continuous, since f is uniformly continuous, on closed interval a comma b, so there exists a delta greater than 0, such that, so whenever distance between s minus s and t is less than delta, implies distance between f of s and f of t is less than, so now it is, I'm taking with respect to eta, with respect to this eta greater than 0, there exists a delta such that modulus of s minus t less than delta implies modulus of f of s minus f of t is less than eta. Now choose a partition say p is equal to x0, x1 and so on up to xn of closed interval a comma b, such that delta xi is less than delta, so it's easy to choose in that way, because by choosing x0 will be a, choose x1 such that the difference is less than delta xi, distance is less than delta, and choose x2 such that the x2 and minus x1 will be difference will be less than delta. And since it's a closed interval a to b and b is finite, so this has to be stops after n steps. Okay, now then if s comma t belongs to interval xi minus 1 and xi, if it is lies between xi minus 1 and xi for I between 1 and n, then the difference between s and t, since they will rise between delta xi minus 1 and xi, their difference will be less than delta xi, hence their difference is less than delta. So this will implies by the continuity, uniform continuity of f, it is f of s minus f of t will be less than eta. Now, so this will implies capital Mi minus small mi is less than eta. What is capital Mi? It is nothing but supremum of f of x in the interval xi minus 1 comma xi, and small mi is the infimum of f of x in the interval xi minus 1 comma xi. See, if you take any 2 points in the interval xi minus 1 and xi, if you take any 2 points in the interval xi minus 1, right, then their difference is less than delta. Moreover, and it implies f of si minus f of t is f of s minus f of t is less than eta, difference between. Moreover, ನೀವು ಯಾವುದೇ ಎರಡು ಎಲಿಮೆಂಟ್ ಡಿಫರೆನ್ಸ್ ತಗೊಂಡ್ರೆ ಅದು ಡೆಲ್ಟಾಕ್ಕಿಂತ ಕಡಿಮೆ ಇರ್ತದೆ. ಈ mi ಮತ್ತೆ ಸ್ಮಾಲ್ mi ಏನು, ದೇ ಆರ್ ದ ಫಂಕ್ಷನ್ ವ್ಯಾಲ್ಯೂಸ್ ಇನ್ ದ supremum and we can say it's a maximum and not maximum minimum, it's the largest and smallest value function value in the closed interval xi minus 1 xi. So ಅದರ ಡಿಫರೆನ್ಸ್ ಕೂಡ ಆಗ eta ಅಥವಾ ಎಟಾಕ್ಕಿಂತ ಕಡಿಮೆ ಆಗಿರ್ತದೆ. So now calculate what is UPF alpha minus LPF alpha. So if it is enough to prove now this difference is less than epsilon to say my f satisfies the Riemann criterion for integrability. Okay, so they are different. This will be now it is equal to Now what is UPF alpha? It is nothing but summation I is equal to 1 to n capital Mi delta alpha I minus what is LPF alpha? It is I is equal to 1 to n small mi delta alpha I. So by taking the common terms, it is summation I is equal to 1 to n. So it is capital Mi minus small mi into delta alpha I. Now what is this delta alpha I? Okay, so yeah, so see, mi minus mi is less than or equal to eta, therefore this one is equal to this one is less than or equal to eta into summation I is equal to 1 to n into delta alpha I. Now what is delta alpha I? See, you have it. Sorry. So this is eta into summation delta. Since mi minus mi is less than or equal to eta implies this one is less than or equal to eta into summation I is equal to 1 to n delta alpha I. Now this sum is nothing but it is equal to eta into alpha of b minus alpha of a. The difference, this sum is nothing but difference between alpha of b minus alpha of a, and eta into alpha of b minus alpha of a, this is less than epsilon, because we choose eta in such a way that eta into alpha of b minus alpha of a is less than epsilon. Therefore we got the difference UPF alpha minus LPF alpha is less than epsilon. So for the epsilon greater than 0, for this epsilon greater than 0, we got a partition P of closed interval a comma b such that the difference UPF alpha minus LPF alpha is less than epsilon. Hence f is satisfy the criterion for integrability. Therefore f is Riemann-Stieltjes integral, that is f belongs to R of alpha on closed interval a comma b. Hence the result. Thank you.